13.8 billion years ago, there was nothing. No space, no time, no matter, no light, not even darkness, because darkness requires space to exist within. And then, everything. In a fraction of a second, so small it has no meaningful comparison in human experience, the universe came into being. Space itself expanded. Time began its forward march. The seeds of every star, every galaxy, every planet, every living thing, all of it encoded in a single, incomprehensible moment. Tonight, we trace that moment and everything that followed, from the first fraction of a second to the formation of the first stars, from the birth of atoms to the slow cooling of a young cosmos finding its shape. This is the story of the Big Bang, the most consequential event in the history of existence. And it is, in every meaningful sense, your story too. Because everything you are began here. To understand the Big Bang, one must first grapple with a concept that resists human intuition entirely. There was no before in any conventional sense. Time itself did not exist prior to this event. The question, what came before the Big Bang, is, in the current framework of physics, as meaningless as asking what lies south of the South Pole. Yet the question persists, because human minds are built to seek causes, to trace effects backward to their origins. The universe's origin sits at the boundary of what science can currently describe, a threshold beyond which our equations break down and conjecture begins. What we do know begins at a moment called the Planck epoch, and from there, the story of everything unfolds. The universe began not with an explosion into space, but as an expansion of space itself. The term Big Bang is, in many ways, a misnomer. It was coined somewhat dismissively by astronomer Fred Hoyle in 1949, a man who actually opposed the theory, and the name stuck despite its inaccuracy. There was no explosion in the conventional sense. There was no center from which matter flew outward into pre-existing space. Instead, space itself expanded everywhere simultaneously. Every point in the universe was, in that first instant, in contact with every other point. As space expanded, those points moved apart, not through space, but along with space as it grew. This distinction matters. The universe didn't expand into anything. It simply became larger, carrying everything within it along as it grew. In the first incomprehensibly brief instant, the universe was smaller than a single proton. At the smallest meaningful moment physics can currently describe, a timescale so brief it defies comparison, the universe occupied a region smaller than a single proton, with temperatures and densities beyond anything that exists in the universe today. At this moment, the four fundamental forces of nature are believed to have existed as a single unified force. What happened at or before this moment remains beyond current theoretical reach. The physics we possess simply cannot describe conditions of such extreme density and temperature. It is the edge of our knowledge, the horizon beyond which mathematics currently fails. Cosmic inflation stretched the universe exponentially in an unimaginably brief instant. In a window of time far shorter than any meaningful human comparison, the universe underwent a period of exponential expansion called cosmic inflation. The universe expanded by a factor so vast that expressing it requires scientific notation, growing from subatomic to astronomical scales almost instantaneously. This expansion occurred faster than light. This doesn't violate Einstein's relativity, which prohibits matter from moving through space faster than light, because space itself was expanding, carrying matter along as it grew, rather than moving through it. The theory of cosmic inflation, developed primarily by physicist Alan Guth in 1980, explains several puzzling features of the observable universe: why it appears so uniform in all directions, why its geometry appears flat rather than curved, and why we don't observe certain exotic particles predicted by high-energy physics theories. Quantum fluctuations during inflation became the seeds of all cosmic structure. Before inflation, the universe existed in a quantum state where energy was not perfectly uniform. Tiny random fluctuations, variations in energy density at the smallest scales, existed throughout the primordial cosmos. When inflation expanded the universe by that extraordinary factor, these microscopic quantum irregularities became macroscopic density variations in the early universe, regions slightly denser than their surroundings, regions slightly more diffuse. Over billions of years, gravity would work on these variations. The denser regions would attract more matter, growing denser still, eventually becoming galaxies, galaxy clusters, and the vast cosmic web we observe today. Every galaxy in the observable universe traces its origin to a quantum fluctuation, smaller than anything currently measurable. As inflation ended, its energy converted to matter and radiation. The field responsible for inflation decayed as the expansion slowed. The enormous energy stored in this field converted into particles and radiation in a process called reheating, filling the now vastly expanded universe with a dense, hot plasma. The temperature at the end of inflation was incomprehensibly extreme, far beyond anything that exists in the universe today. By comparison, the surface of the Sun reaches about 5,800 Kelvin. The conditions of the early universe after reheating were orders of magnitude more extreme. The fundamental forces separated as the universe cooled. As temperatures dropped from inflation's extreme peaks, the unified force that governed the earliest instant began to separate into the distinct forces we observe today. This separation occurred through a series of phase transitions, moments when the universe's properties fundamentally changed, analogous in some ways to water freezing from liquid to solid as temperature drops. Each transition occurred as the universe cooled through specific temperature thresholds, determining the fundamental structure of physics, the rules that would govern everything that followed. The universe we inhabit, with its four distinct forces and particular physical laws, emerged from these early transitions in the first fractions of a second after the Big Bang. Matter and antimatter were created in nearly equal quantities. As the universe cooled through temperatures allowing particles to form, both matter and antimatter appeared in almost perfectly equal amounts. Every quark was accompanied by an antiquark, every electron by a positron. When matter meets antimatter, mutual annihilation occurs. Both particles convert entirely to energy. Had the universe contained perfectly equal quantities of matter and antimatter, every particle would have found an antiparticle. The result would have been a universe containing only photons, no matter, no stars, no planets, no life. But the universe was not perfectly symmetrical. For every billion antimatter particles, there existed approximately 1,000,000,001 particles of matter. This infinitesimal asymmetry, one extra matter particle in a billion, is called baryon asymmetry, and its origin remains one of the deepest unsolved problems in physics. That slight imbalance is the reason the material universe exists. Every atom of every star, every molecule of every ocean, every cell of every living organism descends from that 1 in a billion asymmetry. In the first microsecond, quarks combined to form protons and neutrons. Initially, temperatures remained too extreme for quarks to bind together permanently. They existed freely in what's called the quark-gluon plasma, a state of matter that has been briefly recreated in modern particle accelerators. As the universe expanded and cooled, quarks slowed enough that the strong nuclear force could bind them together permanently. Quarks combined in groups of 3 to form hadrons, primarily protons and neutrons, the building blocks of atomic nuclei. The protons formed in this period were hydrogen nuclei, the simplest atomic nuclei possible. These protons from the universe's first microsecond still exist today, largely unchanged. The hydrogen in water, in biological molecules, in stars, all of it traces to this moment. In the first 3 minutes, the lightest atomic nuclei formed. As temperatures continued to fall, conditions allowed protons and neutrons to fuse together, forming the nuclei of the lightest elements. This process, called Big Bang nucleosynthesis, occurred in a window roughly between 1 second and 20 minutes after the Big Bang. Deuterium nuclei formed first, a proton bound to a neutron, then helium-3, then helium-4. Small amounts of lithium-7 also formed. The process produced a universe whose matter content was approximately 75% hydrogen by mass, with trace amounts of other light elements. This ratio, 3 parts hydrogen to 1 part helium, is one of the most important predictions of Big Bang theory, confirmed by observations of the oldest, most chemically primitive stars. Wherever astronomers look at pristine matter from the early universe, they find this ratio preserved, a cosmic signature written in the first 3 minutes. After the first few minutes of the most violent phase of the universe's creation had passed, nuclei existed. Energy filled all of space, but the universe remained opaque, a dense, glowing fog where light could travel only tiny distances before being absorbed and re-emitted. For the next 380,000 years, the universe existed in this brilliant, featureless state. No stars, no galaxies, no planets, only plasma, slowly cooling, slowly expanding, with the seeds of all future structure embedded invisibly within it. This long period of cooling represents one of the least understood eras in cosmic history, a time before any light that we can observe today could travel freely. For 380,000 years, the universe was opaque. Following the formation of atomic nuclei in the first minutes, the universe entered a prolonged phase during which it existed as a dense plasma, a sea of charged particles so thick that light could not travel more than a short distance before colliding with an electron and scattering in a new direction. This is why we have no direct observations of the universe before 380,000 years old. Light from that era cannot reach us. It was absorbed and re-emitted countless times in a dense fog of charged particles. The universe was not dark during this period. It was blindingly bright, a uniform glow filling all of space. But it was opaque, impenetrable to direct observation even in principle. Recombination freed light and created the cosmic microwave background. When the universe was approximately 380,000 years old and had cooled to around 3,000 Kelvin, roughly the temperature of a red giant's surface, electrons slowed enough to be captured by atomic nuclei. Protons captured electrons to form complete hydrogen atoms. Helium nuclei captured their electrons. This transition, called recombination, occurred with astonishing rapidity across the entire observable universe. As neutral atoms formed, the universe became transparent almost simultaneously everywhere. Photons that had been trapped in the plasma could suddenly travel freely in straight lines across cosmic distances. Those photons are still traveling today, the oldest light in the universe, now stretched by 13.8 billion years of cosmic expansion from visible light to microwave radiation. We call this the cosmic microwave background, and its discovery in 1965 by Arno Penzias and Robert Wilson was one of the most consequential observations in the history of science. Direct evidence of the universe's hot, dense beginnings. The CMB preserves a snapshot of the infant universe. Detailed maps of the cosmic microwave background produced by satellites including COBE, Walmart, and Planck reveal temperature variations of approximately 1 part in 100,000 across the sky. These are not measurement errors, but real physical features, the imprints of those quantum fluctuations from inflation, preserved in the universe's oldest light. Hotter regions in the CMB correspond to slightly denser regions in the early universe, where slightly more matter had accumulated. These overdensities would, over billions of years, grow under gravity's patient influence into galaxies and galaxy clusters we observe today. The CMB is, in a profound sense, the universe's baby picture, a map of the conditions that determined everything that followed. After recombination, the universe entered its dark ages. With neutral atoms formed and radiation streaming freely, the universe entered a period called the Cosmic Dark Ages, lasting from approximately 380,000 years to perhaps 150 to 200 million years after the Big Bang. The universe was filled with neutral hydrogen and helium, slowly moving through space under gravity's influence. The slight density variations from inflation were growing, matter gradually accumulating in the overdense regions, while the underdense regions emptied further. This was the universe's long, patient preparation. Clouds of gas thickening slowly over hundreds of millions of years, drawn together by a force that never hurries but never stops. Dark matter played a crucial role in cosmic structure formation. Ordinary matter, protons, neutrons, electrons, the atoms of everything visible, represents only about 5% of the universe's total energy content. Another 27% consists of dark matter, a form of matter that interacts gravitationally but does not interact with light in any currently detectable way. During the Dark Ages, dark matter's gravitational influence was essential. Because dark matter didn't interact with radiation, it wasn't pushed around by photon pressure during the plasma era the way ordinary matter was. It could begin forming structures, halos of dark matter, earlier, providing gravitational wells for ordinary matter to fall into after recombination. The first structures in the universe were dark matter halos, invisible scaffolding whose gravitational influence directed the flow of hydrogen and helium gas into the regions where the first stars would eventually form. The first stars were fundamentally different from stars today. The very first generation of stars, called population 3 stars by astronomers, formed from gas that contained only hydrogen, helium, and trace lithium, with none of the heavier elements that subsequent generations of stars would inherit from their predecessors. Without heavier elements to facilitate cooling, primordial gas clouds could not fragment as efficiently as modern clouds do. The first stars were consequently massive. Theoretical models suggest typical population 3 stars may have been 100 to 1,000 times the mass of the Sun, though recent research suggests considerable uncertainty about this range. These first stars burned intensely, exhausting their nuclear fuel rapidly. A star 500 times the mass of our Sun might live only 1 million years before exhausting its fuel, compared to the Sun's expected 10 billion year lifespan. They lived violently and died explosively, detonating as supernovae or collapsing directly to black holes. The first stars ended the cosmic dark ages. When the first massive stars ignited, their ultraviolet radiation began ionizing the surrounding neutral hydrogen, a process called cosmic reionization. Over the period from approximately 150 million to 1 billion years after the Big Bang, the radiation from the first stars and early galaxies gradually converted the universe's neutral hydrogen back into a plasma. This reionization transformed the universe from opaque to transparent once more, but in a fundamentally different sense than after recombination. After recombination, the universe became transparent because atoms formed and stopped absorbing photons. After reionization, it became transparent again because atoms were split apart, but the density was now so low that photons could pass through the resulting plasma without significant interaction. The universe we observe today, transparent, filled with galaxies, allowing light to cross billions of light years, is the product of this second transition. Supernovae from the first stars seeded the universe with heavy elements. When population 3 stars died in supernova explosions, they scattered the heavy elements their nuclear furnaces had produced: carbon, oxygen, nitrogen, silicon, iron, into the surrounding gas. For the first time in the universe's history, matter existed beyond the primordial hydrogen, helium, and lithium of Big Bang nucleosynthesis. These heavy elements became incorporated into the next generation of stars and the gas clouds around them. Each successive generation of stars was born from material enriched by previous generations' deaths. Over billions of years and many stellar generations, the interstellar medium accumulated the full periodic table of elements. The carbon in every organic molecule, the oxygen in every breath, the iron in every blood cell, all of it was forged in stars that lived and died before our sun formed. From the quantum seeds planted during inflation, from the dark matter scaffolding assembled during the Dark Ages, from the enriched gas scattered by the first supernovae, the universe began assembling the grand structures we recognize today: galaxies, clusters, the cosmic web. This process of cosmic architecture operated on timescales almost beyond comprehension, with gravity as the patient, tireless architect working across hundreds of millions and billions of years. Galaxies formed through hierarchical assembly. Modern cosmological theory and computer simulations indicate that galaxies did not form as single monolithic structures coalescing from uniform gas. Instead, they assembled hierarchically, small structures forming first, then merging and complaining over time to build larger systems. The first gravitationally bound structures were small dark matter halos, forming within the first 100 million years. Gas cooled and condensed within these halos, forming the first stars and protogalaxies. Over billions of years, these small systems merged repeatedly, collisions and mergers that took hundreds of millions of years each, during which galaxies distorted, stretched, and eventually combined into larger, more complex systems. The Milky Way, with its several hundred billion stars, assembled through this process over roughly 13 billion years, consuming dozens of smaller galaxies, some of which can still be identified as distinct streams of stars in our galaxy's halo. The large-scale structure of the universe reflects inflation's quantum origins. When astronomers map the positions of galaxies across vast cosmic distances, a striking pattern emerges. Galaxies are not distributed randomly, but form a vast network of filaments, sheets, and nodes surrounding enormous empty voids. This structure, called the cosmic web, is the largest organized structure in the universe. extending across billions of light years. The specific pattern of the cosmic web matches predictions derived from inflation's quantum fluctuations. The statistical properties of galaxy distribution today, when traced backward through cosmic time using physics, match the temperature variations observed in the CMB. The connection between the largest structures in the universe and the quantum fluctuations of its first instant is one of cosmology's most extraordinary verified predictions. Large-scale structures represent the largest gravitationally bound structures. At the nodes of the cosmic web sit galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity within clouds of hot gas and dominated by dark matter. These clusters contain more mass in hot gas and dark matter than in their visible galaxies, and they serve as laboratories for studying gravity, dark matter, and the universe's expansion. The most massive clusters contain over 1,000 trillion solar masses and can distort the fabric of space-time sufficiently to act as gravitational lenses, bending and magnifying the light of more distant galaxies behind them, providing astronomers with natural telescopes of extraordinary power. Most of the universe's stars formed between 2 and 6 billion years after the Big Bang. The universe's star formation history follows a recognizable arc. Before the first stellar populations ignited, star formation increased steadily. The peak of cosmic star formation, when galaxies throughout the observable universe were converting gas into stars most rapidly, occurred approximately 8 to 10 billion years ago, roughly 3 to 5 billion years after the Big Bang. Since that peak, the overall rate of star formation across the universe has declined by a factor of roughly 10. The universe is, in a statistical sense, past its prime era of stellar creation. Most of the stars that will ever exist in our observable universe have already formed. The Milky Way formed alongside billions of other galaxies. Our galaxy's history extends back approximately 13.5 billion years, nearly to the beginning of the universe. Its oldest stars, found in dense spherical collections called globular clusters that orbit the galaxy's center, formed when the Milky Way was young and the universe was still being assembled. The galaxy's central supermassive black hole, Sagittarius A star, contains over 4 million solar masses. Evidence suggests it formed early in the galaxy's history and has grown through both accumulation of surrounding matter and merges with the black holes of smaller galaxies absorbed by the Milky Way over billions of years. Our solar system formed from the recycled ashes of previous stellar generations. Approximately 4.6 billion years ago, a cloud of gas and dust in the Milky Way, enriched over billions of years by the debris of preceding stellar generations, began to collapse under its own gravity. The collapse was likely triggered by a nearby supernova explosion whose shock wave compressed the cloud beyond the threshold at which gravity overcomes gas pressure. For approximately 100,000 years, the cloud flattened into a rotating disk as angular momentum conservation drove the collapse inward. The center grew denser and hotter until, approximately 4.57 billion years ago, nuclear fusion ignited. Our sun had formed. The remaining disk material, gas, ice, and dust grains, gradually coalesced into the planets, moons, asteroids, and comets of our solar system. Earth formed approximately 4.54 billion years ago from material that included elements forged in supernovae occurring hundreds of millions of years before our star's birth. Dark energy has governed the universe's expansion for the past 5 billion years. the universe's expansion history has not been constant. For the first several billion years after the Big Bang, gravity's attractive influence was sufficient to slow the rate of expansion. Then, approximately 5 billion years ago, something changed. Observations of distant Type 1a supernovae conducted in the late 1990s revealed that the universe's expansion is accelerating. Distant galaxies are receding faster than they should be if only gravity were operating. The cause of this acceleration, termed dark energy, constitutes approximately 68% of the universe's total energy content. The nature of dark energy is unknown. It may be the energy inherent to empty space itself, Einstein's cosmological constant, or it may be a dynamic field that changes over time. Current observations cannot distinguish between these possibilities. The universe's history we've traced, the inflation, nucleosynthesis, the CMB, the first stars, the galaxy formation, is not merely theoretical speculation. It rests on a foundation of observational evidence accumulated over decades by astronomers working at the boundaries of what technology allows. Understanding how scientists came to know these things illuminates both the history of the universe and the extraordinary achievement of human understanding. In 1929, American astronomer Edwin Hubble published observations demonstrating that distant galaxies are moving away from us with recession velocity proportional to their distance. This relationship, now called Hubble's law, provided the first observational evidence that the universe is expanding. If the universe is expanding now, it was smaller in the past. Run the expansion backward in time, and all matter converges toward a single point at a finite moment in the past. This logical inference from Hubble's observations pointed directly toward the Big Bang, though the theoretical framework to understand it fully took decades more to develop. Georges Lemaire, a Belgian physicist and Catholic priest, had actually derived the expanding universe solution from Einstein's equations in 1927, 2 years before Hubble's observations. But his work, published in French in a Belgian journal, initially received little international attention. Georges Gamow predicted the CMB in 1948, 17 years before its discovery. Physicists Gamow and his colleagues, Ralph Alpher and Robert Herman, calculated in 1948 that if the early universe was hot and dense, as the expanding universe theory implied, it should have been filled with radiation. As the universe expanded and cooled, this radiation would persist, now cooled to a temperature of approximately 5 Kelvin. The prediction was largely forgotten. When Arno Penzias and William Wilson at Bell Telephone Laboratories detected an unexplained microwave signal in 1965, a uniform noise arriving equally from all directions, they initially suspected contamination from pigeon droppings in their antenna. When physicists at nearby Princeton told them they had discovered Gamaw's predicted relic radiation, the CMB became the definitive observational confirmation of the Big Bang. Penzias and Wilson received the Nobel Prize in Physics in 1978. Gamow, who made the original prediction, never received one. Big Bang nucleosynthesis provides a precise test of cosmological theory. The proportions of light elements produced in the first 3 minutes, hydrogen, helium, deuterium, helium-3, and lithium, can be calculated precisely from Big Bang theory using only a single free parameter, the ratio of protons to photons in the early universe. These predictions have been confirmed observationally to remarkable precision. The measured abundance of helium in the oldest, least processed objects in the universe matches theoretical predictions within a few percent. The observed abundance of deuterium in ancient gas clouds matches calculations to similar precision. This concordance between theory and observation across multiple independent measurements represents one of the strongest evidences for the standard Big Bang model. The COBE satellite revolutionized our understanding of the early universe. Launched in 1989, NASA's Cosmic Background Explorer COBE satellite made two landmark discoveries. First, it confirmed that the CMB has a perfect black body spectrum, precisely what theory predicted for radiation in thermal equilibrium in the early universe. Second, it detected the tiny temperature fluctuations in the CMB, the imprints of density variations from the early universe that had been predicted but not yet observed. These fluctuations, at the level of 1 part in 100,000, confirmed that the early universe was almost perfectly uniform, but not quite, providing the seeds from which all cosmic structure grew. COBE's principal investigators, George Smoot and John Mather, received the Nobel Prize in Physics in 2006. The James Webb Space Telescope observes the universe's first galaxies. Launched in December 2021, the James Webb Space Telescope is designed specifically to observe the early universe in unprecedented detail. Its infrared sensitivity allows it to detect light from the first galaxies, shifted to long wavelengths by the universe's expansion. Early results have surprised cosmologists. Webb has detected galaxies at redshifts corresponding to when the universe was less than 400 million years old, galaxies that appear more massive and more structured than theoretical models predicted for such early epochs. These observations are actively challenging and refining our understanding of the universe's first billion years, demonstrating that our understanding of the universe's first billion years remains incomplete. Gravitational wave observatories provide a new window on the early universe. LIGO, Virgo, and CAGRA, ground-based gravitational wave detectors, have directly detected ripples in space-time produced by merging black holes and neutron stars. Beyond individual events, researchers are searching for a background of gravitational waves that may preserve information about the universe's earliest moments. Inflation, if it occurred as theory suggests, would have produced a background of primordial gravitational waves. Detection of this primordial gravitational wave background would be direct observational evidence for inflation, one of the most coveted discoveries in modern cosmology. Particle accelerators recreate conditions of the early universe. The Large Hadron Collider at CERN accelerates particles to energies approaching those of the universe's first microsecond, enabling physicists to study matter under conditions that haven't existed naturally since the Big Bang. Heavy ion collisions at CERN create quark-gluon plasma, the state of matter that filled the universe before protons and neutrons formed. These experiments connect particle physics to cosmology, testing theoretical predictions about the early universe in controlled laboratory conditions. They represent one of the most direct connections between fundamental physics and the origin of the cosmos. Despite the extraordinary success of the standard Big Bang model in explaining the observable universe, profound questions remain unanswered. Some of the deepest mysteries in science surround the events at and before the Big Bang, questions that current physics cannot fully address. The origin of the asymmetry between matter and antimatter remains unknown. As discussed earlier, the universe contains matter rather than antimatter, or rather, the tiny imbalance that favored matter over antimatter ultimately led to a universe of material substance. But the mechanism that produced this asymmetry remains one of the greatest unsolved problems in physics. The standard model of particle physics describes processes that could produce matter-antimatter asymmetry, but not in sufficient quantities to explain the observed imbalance. New physics beyond the standard model is required, and the nature of that physics remains unknown. Experiments at CERN and other particle physics facilities are actively searching for differences in the behavior of matter and antimatter that could explain the asymmetry. The answer, when found, will illuminate one of the most consequential facts about the universe: why it contains something rather than nothing. Dark matter's identity remains unknown despite decades of evidence for its existence. The gravitational evidence for dark matter is overwhelming. Galaxy rotation curves, gravitational lensing, galaxy cluster dynamics, and the large-scale structure of the universe all require the existence of matter beyond what we can see. Dark matter makes up approximately 27% of the universe's total energy content. Yet, direct detection experiments, extraordinarily sensitive detectors buried deep underground to shield them from cosmic rays, have found no confirmed signal. Dark matter has not been produced at particle accelerators. Its identity remains unknown. Candidates range from weakly interacting massive particles, WIMPs, to axions, to primordial black holes. Some theorists have proposed modifying gravity rather than adding new matter. The question of dark matter's identity is one of the most actively pursued in modern physics. Cosmic inflation explains the universe's properties but leaves deep questions. While inflation elegantly explains the CMB's uniformity, the flat geometry of space, and the pattern of density fluctuations, the inflaton, the field responsible for inflation, remains unknown. There are dozens of inflationary models predicting subtly different observational signatures. More fundamentally, if inflation occurred, it likely produced not just one universe, but an enormous number, perhaps infinite, of separate regions, each expanding into its own universe with potentially different physical laws. This multiverse implication of inflation raises profound philosophical questions. If our physical constants are arbitrary values selected from a vast range of possibilities across the multiverse, can they be meaningfully explained or only statistically expected? The boundary between physics and philosophy blurs at this frontier. What happened at the exact moment of the Big Bang remains beyond current physics. The standard Big Bang model describes the universe from approximately 10 to the minus 43rd seconds onward, the Planck time. Before or at this moment, quantum effects would have been significant for the geometry of space-time itself, and no consistent theory of quantum gravity currently exists to describe these conditions. String theory, loop quantum gravity, and other theoretical frameworks offer candidate descriptions of the Planck epoch, but none has been observationally confirmed. The question of whether the Big Bang represents an absolute beginning, a genuine creation from nothing, or a transition from some previous state, perhaps a cycle of expansions and contractions, remains genuinely open. The fate of the universe depends on dark energy's nature. The universe's ultimate fate depends on how dark energy behaves over cosmic timescales. If it remains constant, as Einstein's cosmological constant implies, the universe will expand forever. Galaxies moving beyond each other's observable horizons, stars eventually exhausting their fuel, and the cosmos approaching a cold, dark, nearly empty state in the far future. If dark energy strengthens over time, the expansion could accelerate without limit, eventually tearing apart galaxies, solar systems, planets, and ultimately atoms in an event called the Big Rip. If dark energy weakens or reverses, gravity could eventually overcome expansion, reversing it into collapse, the Big Crunch. Current observations are consistent with a constant dark energy, but the uncertainties are significant enough that other scenarios remain possible. The universe's ultimate story is not yet written. The question of why anything exists at all may be unanswerable. Perhaps the deepest question raised by the Big Bang is not scientific, but philosophical. Why is there something rather than nothing? Even if physicists fully describe the universe's first instant, even if a complete theory of quantum gravity explains the Planck epoch, the question remains why those laws and that beginning existed rather than nothing at all. Some physicists, including Stephen Hawking, have proposed models in which the universe is self-contained and self-causing, with no requirement for an external cause. Others argue that physics can describe what happened, but cannot address why there is something to describe. This boundary between physics and metaphysics is where science reaches its natural limit. From the Planck epoch to the first second, from the Dark Ages to the first galaxies, from galaxy clusters to our particular star in one spiral arm of one galaxy among hundreds of billions, the story of the Big Bang ultimately arrives here, at the atoms that compose this moment, this awareness, this quiet considering of origins. The connection between that first instant and this present one is not metaphorical. It is physical and direct. Every hydrogen atom in the universe formed in the Big Bang's first 3 minutes. The hydrogen in your body's water molecules, the hydrogen fusing in the sun's core, the hydrogen in distant nebulae, all of it formed in those first 3 minutes of cosmic history. These atoms have existed for 13.8 billion years, passing through interstellar space, through stellar nebulae, through the bodies of countless organisms before their present arrangements. The hydrogen in a glass of water carries an unbroken lineage to the Big Bang itself. Every atom heavier than lithium was forged in stellar furnaces. Carbon, oxygen, nitrogen, calcium, iron, the elements of which you are substantially composed, were not present in the early universe. They formed over billions of years in the nuclear furnaces of stars, scattered by supernova explosions and incorporated into subsequent generations of stars and planets. The carbon atoms in your cells were forged in the cores of stars that died before the sun formed. The iron in your blood traces to supernovae that occurred billions of years before Earth existed. You are, in the most literal sense, assembled from the remnants of stellar deaths stretching back nearly to the beginning of time. The light crossing the observable universe carries information across 93 billion light-years. The observable universe, the region from which light has had time to reach us since the Big Bang, extends approximately 46 billion light-years in every direction, for a total diameter of 93 billion light-years. This is larger than the 13.8 billion light-years distance light could travel in 13.8 billion years, because the universe has been expanding during light's journey. Beyond the observable universe, more universe almost certainly exists. The question of whether the universe is finite or infinite remains unresolved, as does the question of whether regions beyond our observable horizon might differ fundamentally from what we observe. The Big Bang story is also the story of information. In the Planck epoch, all information about the universe, every future star, every future galaxy, every future consciousness was encoded in conditions we cannot yet describe. Through inflation, nucleosynthesis, recombination, the Dark Ages, stellar evolution, planetary formation, and biological evolution, that information has been processed, structured, and complexified across 13.8 billion years. The universe began in extraordinary simplicity. It has become, in certain regions, extraordinarily complex. The emergence of minds capable of reconstructing the universe's history from physical evidence represents perhaps the cosmos developing the capacity to understand itself. The Big Bang is the most verified scientific theory in history. From Hubble's 1929 discovery of cosmic expansion to the 2023 data from the James Webb Space Telescope, the Big Bang theory has survived decades of attempts to disprove it and accumulated an extraordinary body of confirming evidence. The CMB's existence, its spectrum, its temperature fluctuations, the abundance of light elements, the observed distribution of galaxy ages and types with distance, seeing older galaxies farther away as the universe's expansion theory predicts, the detection of the first galaxies exactly where theory predicted. No observation has ever definitively contradicted the standard Big Bang model. This does not mean the theory is complete, it is not, but it means it is the best supported description of the universe's origin that human science has ever produced. The story of the Big Bang is still being written. Cosmologists working today are addressing questions that would have been unthinkable a generation ago. The nature of inflation's first moment, the identity of dark matter, the origin of baryon asymmetry, the physics of the first stars, the formation of the earliest galaxies. Each answered question reveals new questions beneath it. The James Webb Space Telescope is actively challenging and refining our understanding of the first billion years. Gravitational wave observatories are opening new observational windows. Next-generation particle accelerators may probe conditions approaching those of the early universe. The story of how we came to be and why the universe exists at all is one of humanity's most profound ongoing investigations. 13.8 billion years. That is the span between the first instant and this one. In that time, from a region smaller than a proton, emerged everything: space, time, matter, energy, forces, elements, stars, galaxies, planets, oceans, life, and the particular arrangement of atoms listening to these words. The quantum fluctuations of inflation became the large-scale structure of the universe. The first protons formed in the Big Bang's first microsecond are still with us, incorporated now into stars, into water, into living cells. The light released at recombination still crosses the cosmos as microwave radiation, the universe's oldest message still in transit. Every element of complexity in the observable universe, every galaxy, every snowflake, every thought emerged from the extraordinary simplicity of those first moments. The universe began with almost perfect uniformity and has spent 13.8 billion years creating structure, complexity, and ultimately the minds that can ask what it all means. That question, what it all means, may have no answer that physics can provide, but the universe's capacity to produce beings who ask it is itself one of the most remarkable facts that cosmology has revealed. If you found value in this exploration, consider subscribing for further journeys through science and history. But for now, consider the atoms that compose you, forged in stars, assembled over billions of years, arranged into the particular pattern of a mind contemplating the origin of everything. The Big Bang didn't happen to you. In the deepest sense, you are a part of it, a local structure through which the universe, for a brief moment, considers its own beginning. Good night.